June 26, 1897. The greatest concentration of naval power on Earth lay anchored off the English coast. More than 100 British warships had assembled at Spithead for Queen Victoria's Diamond Jubilee. Battleships stood in disciplined lines across the water. Cruisers, destroyers, and smaller vessels surrounded them. Their polished guns, towering funnels, and armored hulls represented the strength of the British Empire. This was a carefully organized demonstration. Every ship had its position. Every admiral knew the schedule. Every captain understood the rules. Then an uninvited vessel appeared. It was only 100 feet long. It carried no armor. It had no heavy guns. Compared with the warships surrounding it, the little craft looked almost like a toy. But as naval officers watched, it accelerated. The vessel cut between the lines of the fleet at a speed the Royal Navy's ships could not match. Patrol boats attempted to intercept it, but the stranger simply raced away. Its name was Turbinia, and the man responsible for it was Charles Algernon Parsons. Parsons had not arrived to attack the Royal Navy. He had arrived to embarrass it. The fleet review was meant to show the world that Britain possessed the most powerful navy ever assembled. Instead, one engineer had exposed a weakness. Britain's great warships were powered by machinery rooted in an earlier age. Massive pistons moved back and forth inside their engine rooms. Connecting rods drove shafts. The machinery shook, hammered, and consumed space deep inside the hull. The system worked. But Parsons believed it had reached its limit. His small vessel used something different, a steam turbine. The Royal Navy initially treated the invention as an experiment. Within a decade, that same basic technology would power HMS Dreadnought, a battleship so revolutionary that every major warship built before it suddenly appeared outdated. One engineer had changed how ships moved, and by doing so, he helped Britain create the vessel that triggered a global naval arms race. Charles Parsons had been born into a world of science. His father, William Parsons, the third Earl of Rosse, was an astronomer and engineer. At the family estate in Ireland stood one of the largest telescopes in the world, a machine so enormous that visitors came from across Europe to see it. Charles grew up surrounded by instruments, workshops, mathematics, and mechanical experiments. But he did not become an engineer merely because of his family. He possessed a relentless interest in how energy could be controlled. During the 19th century, steam powered the industrial world. Factories depended on it. Railways depended on it. Ships depended on it. Most engines used steam to push pistons backward and forward inside cylinders. The motion was then converted into rotation. The process was powerful but complicated. Each piston had to stop, reverse direction, and accelerate again hundreds of times every minute. The repeated movement created vibration and placed enormous stress on machinery. Large marine engines could weigh hundreds or even thousands of tons. They occupied valuable space, and there were limits to how rapidly they could operate. Parsons imagined another method. Instead of using steam to push a piston back and forth, he would use it to spin a shaft continuously. Steam would pass through rows of carefully designed blades. As it expanded through multiple stages, it would transfer energy to a rotating drum. There would be no violent reversal of motion, no enormous piston stopping and starting. The rotor would simply spin. The idea of a turbine was not completely new. Engineers had experimented with similar concepts before. But earlier turbines were inefficient, difficult to control, or incapable of extracting enough energy from the steam. Parsons's breakthrough was to divide the expansion across many stages. Each row of blades took a portion of the steam's energy. Together, they converted pressure into smooth, rapid rotation. In 1884, Parsons built one of his earliest practical steam turbines. It was small, but it rotated at an astonishing speed and could drive an electrical generator directly. The machine pointed toward a future in which turbines could produce electricity far more efficiently. Yet Parsons believed the invention could do more than power generators. It could drive ships. That presented a new set of problems. A turbine operated efficiently at very high rotational speeds. A ship's propeller did not. Spin a propeller too quickly, and the water around its blades could begin to form vapor bubbles. The bubbles would collapse violently, reducing efficiency and damaging the propeller. This phenomenon, cavitation, became one of Parsons's greatest obstacles. His early marine experiments did not immediately produce the results he expected. The turbine could generate power, but transferring that power into the water efficiently required a new understanding of propeller design. Many inventors might have blamed the technology and abandoned the project. Parsons kept experimenting. He changed the size of the propellers. He altered their shape. He tested different numbers of shafts and blades. Eventually, he found a solution. Instead of driving one large propeller, the turbine's power could be distributed across several shafts and multiple smaller propellers. The vessel he built to demonstrate the idea was Turbinia. Launched in 1894, it was unlike any ordinary steamship. Its long, narrow hull contained turbines connected to multiple propeller shafts. After further development, the vessel reached more than 30 knots, making it the fastest ship of its kind in the world. But technical success did not automatically produce naval contracts. The Admiralty was cautious. Warships had to survive long deployments, rough seas, and combat damage. A new propulsion system could not be adopted simply because it worked during a short trial. Parsons needed to force Britain's naval establishment to notice. The 1897 Fleet Review gave him that opportunity. Whether the dramatic appearance was quite as reckless as later legend suggested, its effect was undeniable. Turbinia raced through waters filled with the Royal Navy's proudest ships. It moved faster than the patrol vessel sent near it. Naval officers could no longer dismiss the turbine as a laboratory curiosity. They had seen the difference with their own eyes. The Royal Navy soon ordered turbine-powered vessels for testing. Destroyers such as HMS Viper demonstrated extraordinary speed, although early ships also revealed the dangers of pushing new technology rapidly into service. Viper achieved speeds far beyond many contemporary warships, but was wrecked after grounding in fog. Another early turbine destroyer, HMS Cobra, broke apart and sank in heavy weather. The accidents did not prove that turbines were a failure, but they showed that propulsion was only one part of naval design. A fast engine could not compensate for weaknesses in navigation, hull strength, or construction. Even so, the turbine's advantages became increasingly difficult to ignore. It offered greater power from a relatively compact installation. It produced less vibration at high speed. It could drive large ships faster than traditional reciprocating machinery. The technology began appearing in passenger vessels and warships. Then Britain's first Sea Lord, Admiral Sir John Fisher, began planning a battleship unlike anything afloat. Fisher was impatient with tradition. He believed speed could serve as a form of protection. A faster ship could choose when to fight, control the range, and refuse an unfavorable engagement. He also believed existing battleships carried an inefficient mixture of weapons. A typical pre-dreadnought battleship possessed a small number of heavy guns supported by many medium-caliber weapons. At close range, that mixture could produce enormous firepower. But naval combat was changing. Improved sights and fire control methods allowed ships to engage at greater distances. At long range, officers needed to observe where shells landed so they could correct the next salvo. When guns of several different calibers fired together, their shell splashes could be difficult to distinguish. Which gun had produced which splash? Which weapon needed its aim corrected? An all-big gunship promised a simpler and more destructive answer. Every main weapon would use the same caliber. The ship could fire heavier salvos at longer range. Its fire could be observed and corrected more effectively. The idea had supporters in several countries, and experiences from the Russo-Japanese War strengthened arguments for heavy guns and long-range engagement. But Britain possessed the shipbuilding resources and political urgency to turn the concept into reality at extraordinary speed. The new vessel would carry 10 12-inch guns. It would have armor appropriate for a capital ship, and Fisher wanted it to reach 21 knots faster than existing battleships. That speed requirement placed Parsons's invention at the center of the project. Traditional reciprocating engines might have powered a large battleship, but producing the desired speed would have required enormous machinery and created severe vibration. The steam turbine offered a better path. It was still a bold decision. No capital ship had yet relied on turbine propulsion. If the machinery failed, Britain's revolutionary battleship could become an expensive humiliation. Parsons was confident enough to support the technology with guarantees. The Admiralty accepted the risk. HMS Dreadnought was laid down at Portsmouth in October 1905. The British drove construction forward with extraordinary urgency. Materials were prepared in advance. Workers labored under intense pressure. Sections of the ship took shape with a speed intended not merely to produce a vessel, but to send a message. Britain wanted rival powers to understand that even if they copied the new design, British shipyards could build such warships faster. Dreadnought was launched in February 1906 and commissioned before the end of the year. She displaced more than 18,000 tons. Her 10 12-inch guns were mounted in 5 twin turrets. Her armor protected the machinery, magazines, and vital spaces. Deep inside the hull, turbines supplied power to 4 propeller shafts. During trials, the new battleship exceeded 21 knots. The result was unprecedented. Dreadnought combined the striking power of an all-big gun battery with the speed made possible by Parsons's turbines. Existing battleships had not physically changed. Their armor remained just as thick. Their guns remained just as dangerous. But strategically, they had been pushed into an older category almost overnight. A pre-Dreadnought might carry 4 12-inch guns. Dreadnought carried 10. An older battleship might struggle to reach 18 knots. Dreadnought could exceed 21. She could deliver a heavier long-range salvo and potentially control the distance of an engagement. If an older ship attempted to close the range, Dreadnought could use her speed to stay away. If the older ship attempted to retreat, Dreadnought could pursue. The transformation was so complete that naval language itself changed. Ships built according to the new model became known as dreadnoughts. Everything before them became pre-dreadnoughts. Britain had created the most advanced battleship in the world, but it had also created a serious strategic problem. Many of those ships were now considered outdated. The new design had reset the competition. Britain held the first modern dreadnought, but Germany and other powers could now build similar vessels. The race would no longer be measured by the total number of older battleships. It would be measured by how many dreadnoughts each nation could construct. Germany responded. The United States responded. Japan responded. Naval budgets expanded. Shipyards grew. Guns became larger. Armor became thicker. Dreadnought had not ended the competition for naval supremacy. She had intensified it, and turbines became a crucial element of the new generation. As naval engineers gained experience, turbine-powered warships became larger and more capable. Parsons continued improving his machinery. One major challenge remained fuel economy. Early direct drive turbines performed well at high speed, but were inefficient when cruising slowly. Their rotors wanted to spin rapidly, while propellers operated best at lower speeds. The development of reduction gearing helped solve the problem. A turbine could rotate at an efficient high speed, while gears reduced the rate transmitted to the propeller shaft. This allowed later warships to combine powerful turbine machinery with improved cruising performance. The influence spread far beyond battleships. Cruisers, destroyers, ocean liners, and eventually aircraft carriers adopted turbine propulsion. Parsons had not simply made one vessel faster. He had changed the relationship between machinery and naval strategy. Speed affected where a fleet could operate. It affected how quickly forces could concentrate. It influenced whether a commander could pursue, withdraw, or control the distance of battle. In a carrier task force, speed would later help ships maneuver into the wind to launch aircraft. In destroyers, it enabled rapid attacks and screening operations. In battlecruisers, it became a defining feature of the entire design. But HMS Dreadnought's own combat career was less dramatic than the fear created by her appearance. She did not destroy an enemy battle fleet. She missed the Battle of Jutland in 1916 because she was undergoing refit. Her most unusual success came in March 1915, when she rammed and sank the German submarine U-29. It was a strange victory for a vessel designed to transform long-range battleship combat. The battleship that had made other capital ships obsolete destroyed its only confirmed enemy by striking it with the hull. By the end of the First World War, Dreadnought herself had already been overtaken by newer ships. Later battleships carried heavier guns, improved armor, better fire control systems, and more efficient turbine arrangements. That was the cost of creating a revolution. Once the world accepted Dreadnought's principles, development moved so quickly that the revolutionary ship became outdated within its own lifetime. She entered reserve in 1919. A few years later, she was broken up. The vessel that had forced the world's navies to rebuild was herself reduced to scrap, but the idea inside her survived. The all-big gun battleship would dominate naval planning for decades. Steam turbines would power generations of warships and merchant vessels. Even when battleships lost their central position to aircraft carriers, turbines continued driving the new giants of naval warfare. Later, nuclear reactors would replace coal and oil as the source of heat in some ships. But the reactors still produced steam, and the steam still turned turbines built on principles Parsons had helped establish. The journey from Turbinia to Dreadnought had begun with an engineer refusing to accept the limits of the piston engine. Parsons did not command a fleet. He did not fire a gun in battle. He did not design every part of Dreadnought, nor did he alone invent the concept of the all-big gun battleship. Admiral Fisher supplied the institutional force. Naval architects shaped the hull. Gunnery experts developed the weapons and fire control ideas. Shipyard workers transformed drawings into steel. But without propulsion capable of delivering the speed Fisher demanded, Dreadnought would not have become the same revolutionary weapon. Parsons gave the battleship more than an engine. He gave it mobility. His turbines allowed thousands of tons of armor, guns, ammunition, coal, and machinery to move faster than any comparable battleship. That speed turned Dreadnought from a heavily armed experiment into a strategic threat. 9 years before the ship was commissioned, Parsons had driven a tiny vessel past the assembled pride of the Royal Navy. The admirals watching from their anchored warships saw an irritating little craft cutting through the water. What they were actually seeing was the future. Turbinia carried no armor and almost no weapons, yet it possessed the technology that would help redefine naval power. The old battleship had been built around massive pistons, mixed-caliber batteries, and assumptions inherited from an earlier age. Dreadnought combined uniform heavy guns with turbine speed. In a single ship, Britain changed the standard by which every battleship on Earth would be judged. And behind that transformation stood a quiet engineer who had once been forced to crash a royal celebration simply to make the Navy pay attention. Charles Parsons did not merely build a faster engine. He created the machinery that helped turn the battleship from a slow armored fortress into the most feared naval weapon of its age.